We'll start with the historical perspective of quantum mechanics. Historically, there were particles, things that had mass and velocity, therefore that could generate momentum and kinetic energy. And there were waves, things that had wavelength and frequency. They diffracted and they interfered with each other. Classically, there was a firm boundary between these two types of physics. However, 4 key experiments changed this. There would be experiments performed by Max Planck, Ernest Rutherford, Albert Einstein, and Niels Bohr. We will start by looking at the work of Max Planck, who investigated the theory behind what were known as black body radiators, essentially the first lasers. These were hollow metal spheres that had a pinhole drilled in them. They were then heated up to very high temperatures. Since they were black bodies, essentially colored black, there was total internal reflectance. Only waves of the correct wavelength could escape the pinhole. The size of the radiator determined which wavelengths would be in phase when exiting the hole. The alignment with the pinhole collimated the waves, and the size of the pinhole selected the frequencies emitted. This led to collimated light of a single wavelength, and higher temperatures differentiated the color as the wavelength was proportional to the temperature. Planck attempted to model the behavior of the blackbody radiators by curve-fitting the experimental data. This work had been begun by Ludwig von Boltzmann. He approached the problem by applying what are called Lagrange multipliers, essentially scalable dummy variables. In his work, the radiant energy density, nu sub v, was equal to an unknown variable a times the frequency cubed, e to the minus beta, another unknown, times the frequency over t. As you see, he did not perfectly match the experimental data, nor did he solve for alpha and beta. Planck refined Boltzmann's work. He defined the radiant energy density as alpha nu cubed divided by e to the minus b nu over t minus 1. Again, visually, you can see this perfectly matched the experimental data. Additionally, Planck solved for alpha and beta. His final solution, rho sub v, was equal to 8 pi times a constant called h, nu squared, over the speed of light cubed, times the frequency divided by e to the minus h nu divided by another constant kt minus 1. In this solution, alpha is equal to 8 pi h nu squared over c cubed, and beta is equal to the new constant h divided by k. In this solution, k is Boltzmann's constant. It can be found by dividing the gas constant by Avogadro's number and has a value of 1.38 times 10 to the minus 23rd joules per degree Kelvin. It represents the potential energy of one particle, and it was already known and classically derived. H was something new. We know it as Planck's constant. It has a value of 6.626 times 10 to the minus 34th joule seconds. It is not based on motions or waves or other classical phenomenon and was required to fit the experimental data. Planck called this poetically the quanta of action of the universe. Planck had discovered the universe has inherent energy not derivable from classical physics. We next look at the work of Ernest Rutherford and his graduate students in the Geiger-Marsden gold foil experiment. In this experiment, an alpha particle, a helium nucleus, is accelerated at a sheet of gold. Gold is amazing. It is the most malleable of metals. It can be mechanically beaten to a thickness of 1 atom thick, which is how gold leaf is applied and why it was particularly important to this experiment. The expected result was compared to firing a shotgun into a tissue. It was expected that obviously the alpha particle would pass through the foil, and it would also blow a big hole in the foil. The actual result is what astounded. The alpha particles did indeed pass through the foil, but not in a straight line. The alpha particles scattered after passing through the foil, and most surprisingly, the foil was left intact with no hole. Rutherford concluded, based on this, that matter is mostly made up of empty space because the alpha particle is able to pass without causing any damage, and the nucleus is positively charged because the positive alpha particles were scattered after encountering the nucleus. Next, the Nobel Prize-winning work of Albert Einstein on the photovoltaic effect. It was known from the work of Max Planck that light has energy, and that energy is equal to Planck's constant times the frequency. The question Einstein was investigating was, can light transfer that energy? In this experiment, light of a given wavelength is shown upon a metal. An electric current was produced. An electric current is the moving of electrons, and it was the light that caused these electrons to move. As known classically from Newton, an object at rest will remain at rest unless acted upon by an outside force. It is also known that force is mass times acceleration. Since the electrons were at rest, and the light was the force that provided the force that caused them to move, that meant light has mass. The universe, therefore, has a dual nature. Everything that exists acts as both a particle and a wave. Additionally, Einstein discovered that electrons are not actually tightly held to the nucleus. He developed a relationship, knowing that the energy of light was equal to Planck's constant times the frequency, that had to be equal to the total energy of the relationship, which he denoted as phi plus 1/2 mv squared, the energy of the moving electron. His variable phi, which he called a work function, is actually the first ionization energy of the element. Finally, we look at the work of Niels Bohr in his investigation of the atomic spectrum of hydrogen. Hydrogen, as you know, is the simplest element with an electron configuration of 1s1. As with all elements, when heated, it emits a characteristic light. In the case of hydrogen, this light is yellow. The expected result was that yellow is a primary color, as you know, and therefore, when this light is shown through a prism, no change should occur. The actual result was that the prism split the yellow light emitted by the hydrogen gas. More importantly, it split it into distinct, sharp, and discrete wavelengths. Again from Max Planck, Bohr knew that the energy of light was equal to h nu, or h times the speed of light over the wavelength. Since multiple wavelengths were produced, multiple energies had to exist. However, hydrogen only has one negative electron and one positive proton. Therefore, there should only be one possible interaction. Bohr deduced the only way to get multiple energies is if the one electron had multiple distinct distances that it could occupy from the nucleus. And therefore he concluded electrons travel in distinct orbits around the nucleus. Niels Bohr formulated his theory on atomic orbitals as follows. The electron orbits the nucleus. Multiple paths are available. Each one is at a distinct and discrete distance. These are possible orbits. Upon heating, an electron would rise to a higher energy level, therefore a higher orbit. Multiple paths are open for that electron to relax back down to its ground state. It could drop from 4 to 3 to 2 to 1, from 4 to 2 to 1, from 4 to 3, and from 3 to 1, and so on. Each of these paths travels a different distance. Each different distance yields a different energy. Each different energy will emit a different wavelength. Mathematically, Bohr found the following relationship. The light of the energy absorbed, delta E, h nu, is equal to a constant called the Rydberg constant, 2.18 times 10 to the minus 18th joules, times 1 over n low squared, where the electron ended up, minus 1 over n high squared, where it fell from. This formula worked perfectly for predicting hydrogen transitions. However, it doesn't work for any other element. Therefore, there are more relationships than distance that need to be investigated when determining the energy of an electron. So, concluding this historical overview of quantum mechanics, Max Planck determined that light has energy, and the energy of that light is equal to Planck's constant times the frequency. Ernest Rutherford, through his gold foil experiment, determined matter is mostly empty space, and the nucleus is positive. Albert Einstein determined that light also has mass, and since it behaves both as a mass and a wave, the universe has a dual nature. And finally, Niels Bohr deduced that electrons travel in discrete orbits and that energy is quantized. The result of this is something that you already learned in freshman chemistry, so you should always trust what you already know. You know there are more than one type of motion possible for an electron, and that reality is defined by 4 quantum numbers. The first quantum number, n, can have any positive integer and is the principal quantum number, meaning it gives you the energy level or the row on the periodic table that a particular electron would fall into. The second quantum number, L, can have any integer value from 0 to n minus 1. It is called the angular momentum quantum number, and it defines the shape of the orbit and the column on the periodic table. Your third quantum number, m subscript L, can have any integer value from negative L to positive L. It is called the magnetic quantum number. It gives the direction of the orbit and the number of suborbit or orbitals that are possible. And finally, you have m subscript s, or m sub s, which, if you remember, has values of plus a half or minus a half, and defines the spin of the electron, which can be either clockwise or counterclockwise. You will note these numbers are related to each other. N is related to L. Therefore, if n was 4, L could be 0, 1, 2, or 3. These would define the s orbit, the p orbit, the d orbit, or the f orbit. Additionally, m sub L is related to L. So if L is 0, m sub L can only be 0. This means there is only one s orbital. However, if L is 1, m sub L can be -1, 0, or +1. 3 values denote that there are 3 p orbitals. If L is 2, m sub L could be -2, -1, 0, 1, or 2. 5 values means the d level holds 5 orbitals. And if L is 3, m sub L could be -3, -2, -1, 0, 1, 2, or 3. 7 values from m sub L mean there are 7 f orbitals. Another way of looking at this: your principal quantum number, which gives the distance from the nucleus, provides a potential energy. Therefore, in orbit, the kinetic energy has to balance out this potential energy. Hence, m sub L is related to L, and L is related to n. You may also remember from freshman chemistry, the Pauli exclusion principle said no 2 electrons can have the same 4 quantum numbers. Since your final number m sub s has only 2 values, +1/2 and -1/2, that means each orbital is restricted to holding 2 electrons. Since there is one s orbital, there can only be 2 s electrons, the first 2 columns on the left side of the periodic table. 3 p orbitals can hold 6 p electrons, the 6 columns on the far right side of the periodic table. 5d orbitals will hold 10d electrons, the 10 transition metals in the middle of the periodic table, and 7 f orbitals would hold 14 f electrons, the 14 columns of lanthanides and actinides at the bottom of the periodic table.